Okay, so shall we start?
Yes, let's start. So,
Okay. Okay, so uh, yeah, so there are this final last 4 weeks, right? So this is largely about text data. Okay, so text data and problems based on text data. So that is what the last 4 weeks are about. Okay, so you must always keep this point in your mind. Okay, that this is about the last 4 weeks. Yeah, so YouTube link I will upload it once I'm done the session. I'll upload it. Okay. So what do I mean by text data? It's actually sequential data, right? So the reason being text is a sequence of words, right? So text is nothing but a sequence of words. So whatever we do now will apply not just for text data, but also for any data that has some kind of sequence information. So text is a sequence of words. What else is a sequence of words? You have what is called time series data, right? So you have, this could be stock prices, rainfall over a period of days, months, years, right? Rainfall patterns. So that is also sequence data. You could also have videos, right? So where someone is performing some activity, so you have these problems called activity recognition, where you want to know what is happening, right? It could, some use cases would be like, is there some suspicious activity? So you have these CCTV cameras, right? So you get the feed from CCTV cameras, let's say especially in front of airports and critical locations, and you want to find out, you want given a video stream of say 1 minute, you want to find out if some suspicious activity is happening or not. Okay, so that's a binary classification where your input is a stream of data. So videos are essentially nothing but images. Okay, several images make up one video, right? So we call them frames, right? Each image we call them frames. So whatever videos you see on YouTube or any other channel, right, any other streaming platform, it's actually nothing but thousands of images that are relate to you one after the other in such a quick succession that your eye is not able to distinguish one frame from the other. So it seems continuous, right? So it seems continuous, but in reality it is discrete, right? So this is something you have to appreciate. The whole thing is discrete, so it's made up of a finite number of frames. So this is what you call the frame rate, right? So you, different videos have different frame rates. If the frame rate is very low, let's say 5 frames per second, then you might be able to see, these are like the cartoons of your old, right? You might be able to see individual actions, individual frames even. But if your frame rate is really high, then you'll not be able to distinguish different frames, one frame from the other, right? So it'll all seem continuous, but ultimately, what is a video? What are rainfall patterns, stock prices? These are all sequential data, right? And they come in. There is what is called a temporal nature to all of this, right? So temporal nature meaning there is time, right? So we will see in all, in the way we represent data, we'll see this subscript T entering, right? So the subscript T so far, where have you seen the subscript? We have seen WT plus one and all that, right? So we have seen, why did we need subscripts for weights? Because we were doing iterative algorithms, right? Gradient descent, stochastic gradient descent. They were all updating the weights, and there was some temporal nature to it. So start with some weights and then you update it. But we never had XT, YT, right? So we never had to label our data points with time, right? So, but then that was because we were not dealing with data as sequences, right? So far we have only discussed what images maybe for the CNN weeks, and before that we didn't even say what our data looked like. Our data was just some matrix. You are passing some matrix to a feed forward network and you are getting some output. Okay. And a matrix is just a collection of data points. There is no relationship between, let's say, the third data point and the fifth data point, right? So they are all drawn IID from some distribution. That's the assumption so far. But now that's no longer the case, right? Slowly you see structure entering. So in a CNN, so or rather in images, the structure was spatial, right? So you one part of the image, if you take the image of a human face, one part of the image had some resemblance to the other part. So for instance, I have said this before, if you look at the forehead, the pixel values are all going to be somewhat similar, right? Because the forehead is one continuous block. Okay, so there is a spatial structure that is present in images, and this was exploited using sliding filters, right, or kernels. That was the whole idea behind convolution operation, right? So you could, because there is this spatial structure, you could make use of that using sliding filters, and these filters will recognize different shapes, different elements of the image. Okay, so in the case of or rather in the case of text data or sequence data, the structure is what we call temporal. Okay, there's a time temporal, meaning there's a time dependency. Okay, so what we will look at is neural networks that are able to exploit this temporal structure. Okay, so that is what we will eventually look at in the form of recurrent neural networks. So the networks that were developed to make use of this temporal structure, they were called RNNs. Okay, they are called RNNs. We'll maybe look at them tomorrow or maybe next week, early next week. Okay, but today what we'll do is focus on how to represent, so representing text data. Okay, so that's what is kind of important now. Okay, so far are there any questions?
No, sir.
Okay, right. So there are okay, maybe before we even look at representing text data, I'll just continue. So this will be slightly non-linear, right? So I won't exactly cover week 9. I'll just, sometimes I might jump to some parts of week 10, week 11 because they are relevant. So I've told you that sequence data is what we'll be looking at in the last 4 weeks. And a good representative of sequence data is text data, right? So text comes in the form of sequences. So we look at some important problems in the domain of text data, right? So we call this natural language processing, right? Because this whole domain, whatever last 4 weeks we are seeing, is actually natural language processing, meaning you are working with language. Okay, it's called natural language as opposed to machine language, right? You are looking at language as it is spoken by you and me. Okay, and the whole goal of NLP is to try and understand text that occurs in the natural setting. Okay, so what has happened is in this field of NLP, we have looked at multiple tasks, right? So there are so many tasks that we have looked at. I'll just list some of the most important tasks that the community has focused on. So one of the simplest is what is called sentiment analysis, right? Uh, so what is this? Can someone tell me what this task is about? Do you have any
Analyzing
video?
the sentiment of the words
Yeah,
said.
yeah, exactly. Right. So you have a movie review, let's say. So you have a movie review, and that can be, you would like to know whether that movie review is having a positive sentiment. So good movie, great movie, outstanding movie, good characters, good plot, screenplay, right? So those are positive sentiments, and you could have negative sentiments, right? So the movie was trash, it was boring, it was too long, it wasn't that good, right? So you notice the complexity. So if you have things like it was not that good, right? So you can see how difficult it is for a computer algorithm to figure this out, because the word good is usually associated with a positive sentiment, but then you have a negation, right? So a good algorithm could be a neural network, it could be something else, has to figure out this part that good is positive, but then because not comes before that, the entire sentiment is negative, right? So this is a hard task. So what you have to understand is this is a hard task for machines to master. Okay, so you have a positive, uh, negative. Okay, you could call this up. You could treat this as a binary classification problem. So input will be some text, and then the output will be a label, positive or negative. Okay, so this is a very classic problem. Um, Next, you have other classification tasks. So you could have text slash document classification. So this is again a very classic example where you have different documents, and you might want to say you are in a newspaper setting, a modern newspaper setting where you you have different articles with you, and you would like to classify them based on the genre, right? So genre, maybe there are 10 classes. So this is business, then this is politics, and whatever, right? So some 10 classes, dot dot dot. I hope you sports, right? So you will here the input will be again a piece of text, but it may not be as short as a movie review. It may be a longer piece of text. Okay, so that is something that will come in. Another example of text document classification. This is historically this came. This was one of the first applications of NLP, right? Spam detection. So you have spam versus ham, right? This usually we call it spam versus ham. We continue to receive spam messages and mails, right? So it's again binary. So given a document or given a message, predict the class. Okay, so this is a very important usage. We actually have these spam filters present in Gmail, right? If you think about it, you have a separate spam folder. Even without you knowing, there is some algorithm, some ML algorithm running in the background that can detect if a mail is spam or not. Okay, so these are all examples where the input is text and the output is a class label, right? So you could call these, if you want to classify them, these are all uh, input is text, output is a label, right? It's a single label. Uh, but now we look at few more applications which are not so straightforward. If you think about it that way, so input here will be text again. Okay, and so I'll maybe instead of calling it a label, I just say some category, right? So it's a review or it's a document category. So here input is text, output is also text. Okay, these are by far the more interesting or real world applications. If you think about it, these are the more interesting ones. So historically, once again, a source of great interest for the research community has been machine translation. We call this machine translation. So your Google Translate is an example of machine translation, right? Google Translate, what does it do? It takes input in one language, and your output should be, so we could call this, generally call the source language, and the output is in target language, right? So how do you train this system? You would give it, it's a supervised learning problem, right? So you would give it pairs of input, you will give it input output pairs. Input will be in one language, the output in the target language. You will train it, and then you will see if it performs well, right? So it's here, notice that this is something that we have never seen before. So far in our CNNs and in our feed forward networks, we know how to do classification. Okay, so we can do this. We kind of know how to do this. We also know how to do this, right? Spam versus ham, or this is just multi-class, business, politics, sports. I have a mental model of how to do this, but we kind of don't know how to produce text, right? So how do we even think about that? Okay, so you'll have to keep this in your in the back of your mind. So how do we continuously output text? Okay, this seems like a new problem altogether. So other tasks very common in the NLP community is called summarization. So you have a piece of text, a document, and you have to output the summary. Okay, so input is going to be a large body of text. Output is going to be text again, smaller body of text. Okay, that contains the essence of the original document. So this is summarization. You also have a few other categories which are popular in the community. It's called question and answering, where you will ask you the query, you'll send a query to the system, and the system has to respond with an answer. Okay, these are much shorter than summarization. They'll be like single word summary, single word answer, or just 2 or 3 words. Okay, something like your KBC types. Okay, and you have dialogue systems. So we are now nearing our chat GPT kind of thing, right? So dialogue systems are even more complex. So at least here you know that the output will stop after one round, right? So here it's kind of back and forth. Okay, so dialogue systems are a much more complex class of problems. And what else we have? So finally, perhaps should come before. We have what is called language modeling. Okay, so this language modeling is a very ancient problem, and it's a very interesting problem. So it's dry to state, but then what you see around you, you'll be amazed to see that almost all these problems have now been solved just because we have managed to do this properly. Okay, so language modeling is a very simple task. So what we do here is give a set of words, okay, sequence of words as input. Okay, the input is a sequence of words, and the model should output the most probable word. Okay, that follows this sequence. That is all there is to language modeling. So this particular kind of modeling is called an autoregressive language model. So most of your chat GPT, Gemini, and whatever you're using, they'll all come under this class of language models. So once you figure out how to do language modeling really well, then you can very easily extend it to dialogue systems, Q&A, summarization, translation, all these. Okay, so this is a class of learning called semi-supervised or self-supervised learning. Okay, where the labels are going to be present. So you don't. So how do I put this? You don't need someone to label the data for you. Okay, it's a great advantage. So if you have a piece of text, okay, the label is there in the text itself. So that's what it means to say that it's self-supervised. So far, if you go back, let's see what I mean. I'll just tell you what I mean by this. So in the case of sentiment analysis, what is the label? The label is positive or negative, and it is not there in that piece of text. You need to have someone sit and read the reviews and then label them. So labeling is manual, right? So that's why this is a classic supervised learning problem. So the supervision or the labels come from someone else external, right? Same for text document classification. But then if you come to language modeling, thankfully the text itself has the labels. Okay, so that's why this is called self-supervised learning. We will see all this is a part of syllabus. Okay, so I'm not going outside syllabus. So you will see this in week 12. So you will see what is called transformer. Transformer is the architecture that realizes a language model. We'll see a language model today also, but it's not a complex language model. It's a simple one. Okay, so that's a summary of problems in natural language processing. So any questions so far?
So can you give one example of that self-supervision?
Okay.
How like the label
Yeah.
and
So what I mean by self supervision is, okay, let's say you want to learn a language model. So language model is, uh, what is a language model? You give it a sequence of words. It should predict the most probable next word. That is a language model. Simplified idea. Okay. So how do you train it? You train it by passing it a large corpus, a huge corpus of data. So we call it a corpus. Corpus is nothing but some piece of text. Okay. So we call it corpus. Plural is corpora, right? So huge corp, you pass huge corpora to it. Uh, okay. So what is commonly done is they pass the entire Wikipedia. Right? Okay. So the entire English Wikipedia is passed. That is one of the sources of text. And so this is input. Okay. So this is the data set. How does a training example look like? So let's let me take some document from Wikipedia, right? So let's see.
Sir,
Yeah,
so in this form, it will take all the sub sequence of sentences and it will train one by one. Like that, it will be
exactly. Yeah. So it'll not just entire sentence. Uh,
I mean, two words, at least two words it should have. Right?
yeah,
Then only it will be able to give what is the previous word so that it can predict the next one.
yeah, yeah. So let me just give a very quick example. So I have, hmm, I have a piece of text. Okay. So I just copied this from. This is a part of the training corpus. Okay. This is a piece of text. So what it will do, how you will train these models is as follows. So you will start from left to right, okay, and you will consider a window of text. Okay, this is a sliding window. So let's say you choose a window of length 1, 2, 3, 4, 5, 6. Okay, so this is one example. Okay, so this is the input. So if you pass this as input, the model should predict who. Okay, so another piece of input would be you will just start sliding this across the whole. So we started here, right? In fact, we have to start from here, but just I hope you get the idea. So I start from here and I'll give this as input and I'll train my model to predict is. Okay, so the reason this is self-supervised is because the labels are drawn from the corpus itself, right? No external agency is called on to label the data. Okay. Do you understand what self supervision is?
yes, sir. And sir, but like the word "who" is predicted. If there are two words with the same probability, then how it will choose which one to put next?
So that is, so there is, you will study about this. There is, now it might not be the right time. So there are concepts called teacher forcing and student. So when you're training a network a language model to predict, you could do what you typically do is uh, you train it to predict whatever is there in the original corpus. Okay, so when you're, so there are two things, right? So you have to distinguish between, so you have to distinguish between the following: training phase and inference. Okay, so during the training phase you are not expecting the model to return a prediction to you, right? So you're just going to find the loss incurred in predicting who. Okay, that's what you'll minimize and back propagate, right? So in the training phase you are not really bothered about the exact word that it predicts. It's only during inference or during testing that you care about the exact word it predicts. So here different strategies are used. So the situation that you mentioned will rare. It's very rare that two words will have the same probability, but there are different sampling strategies, right? So So we'll come to that when we actually do inference on language models. Okay. Just
sir.
yeah, you can remind either me or Manoj. We'll discuss about. So there is something called beam search. There are different strategies to, see what word your language model will output. So if you look at ChatGPT, if you give the same prompt to ChatGPT, it won't give you the same response always, right? So that's because it doesn't return the maximum probability word. It does something called sampling. So it's sampling from a probability distribution. That's why it doesn't return the same sequence always. Okay, so yeah, so I hope you got an idea of what NLP is and what we'll be doing in the next 4 weeks. All right, okay, so now we can start with representing text data. So I hope I have convinced you that text data is a very important thing that we have to study. So the question now becomes, how do you represent text data? So images we represent using pixels and of the form image volumes, right? So you have W cross H cross D. Okay, and then you pass it through some CNN and you know what to do. It's very straightforward for images, no confusion. But how do you represent text? Okay, so the first thing that you do is when you have a corpus, as I said, corpus is some large body of text, okay, having multiple sentences. So what you do is you first extract what is called the vocabulary. Okay, so the vocabulary is nothing but the set of unique words in a corpus. So, for example, let's say this is your corpus. Hmm, tell me some sentence. Some random sentences, right? So let's say our corpus has three sentences.
Sir, you are a good teacher.
Okay, you are a good teacher. Okay, so those are maybe tell me one more so that there are some repetitions.
Real is hardest subject.
Okay, something. So what I want is something where there is a repetition of words from here. So the teacher saw a cat near his home. Okay, something like this. Okay, so this is your corpus. So this is a typical corpus, very simplified corpus, but this is how it looks like. Now what you do is you first extract the vocabulary. Vocabulary is a set of all words that are present in your corpus, right? So in this case, you have the cat sat on the is already counted.
Sir, set of word means you mean duplicate would be removed, right?
I removed the duplicates, right? So only the unique. So how many words are there? That unique collection, right? So you just, if in Python terms, take this list of words, pass them through a set function, set constructor, you will get them. Okay, so home, U is new, R is new, good is okay, maybe I'll just say the good old cat. Okay, so old is also there now. U I have added, R good I have already added, teacher is new, the is already taken, teacher is also already listed, so saw is not there, so cat is already there, near is new, his is also new, home is already there. Okay, home is recorded here. Okay, so now you count the number of words. So how many are there?
19 words.
19, huh? Okay, so we call this the vocabulary. So open curly braces, set notation, right? This is the vocabulary, and we say that the cardinality of this is 19, right? So the set size of the vocabulary is 19. Okay, this is how you build a vocabulary. So this is building a vocabulary. You'll have to do this even so everyone who has built language models, right, or who is currently building a language model, this is one of the first steps that they'll do. So they'll collect a big, huge corpus. So comprising of Wikipedia dump and so many books, Google books, whatever, whatnot, right? So they'll collect all of that. They'll actually clean it. So there's a cleaning process that will happen where you kind of parse that data and make it clean enough for consumption. Then you will build a vocabulary. Okay. So typical vocabulary vocabulary sizes are, say, the order of 10,000, 50,000 words. Okay. Okay, so that's what you do. So once you have a vocabulary, what you can do is now the question. So remember, the question that we are interested in is how do we represent text? Okay, more precisely representing words. Okay, text is nothing but a sequence of words, right? So how am I going to represent words? So my computer doesn't understand any of these things, right? So I need to convert them to numbers, and one way to do that is one-hot encoding. We have already seen this for labels. So for multi-class classification, we saw one-hot encoding, but then we are now going to see how that can be used for text also, right? So let's say he's going home. Now the question is, how are we going to represent each word here, right? So how will he be represented? He will be represented by having a one wherever he is. Okay, so you can now think of this as coordinates, right? So there's no cat, there's no sat, there's no on, there's no mat, there's no, okay, there is a
Single words it will represent, or total sentence it will be representing in one hot.
sorry.
No, it will be representing one hot encoding will represent the entire sentence, right? Not the word.
No, just the word, right? So we are actually representing individual words, and then a collection of words will represent a sentence.
Okay, so feeding to the system, it will be in words or sentence. Like for example, for he, it will be assigning one value. Next one is there. The place where is there, it will be assigning one. Next,
Yeah,
when going is
correct.
like that
Yeah,
only,
yeah.
right?
So it will be, so that's a one hot encoding, right? So you are going to have one hot encoding for words. So I get what you're saying. So if you want a single vector for a sentence, you could do that. So wherever these 1 to 4 words are there, you'll have ones. So you'll have 4 ones, rest are zeros. But we are talking at the word level. Okay, sentence level comes later. So this is the word level. So I'll just maybe call this it's a arrow. Is there a vector arrow? Yeah, it's there. So this is going to be the he vector, right? So this will be 0 and then many zeros. Okay, I'm not writing the whole thing. This will be one vector. Now, likewise, I hope you get the idea. So going will be another vector. Okay, so I'll represent it as 0, many zeros. Wherever going is there, that will have a 1, and rest of them will be zeros, right? So what is the problem with this approach? Do you see any issues? Okay, so this is not very expressive. Okay, so this is discussed in the lectures already. So you if you want to compare two words, okay, there is no way to do that. Okay, so any two words, if you take let's say, so teacher and his, right? So what is his here with respect to teacher?
Subsequence of
So is it a pronoun? Do you recall what pronouns are?
yeah, it's a pronoun to mention
Yeah,
the
so this
teacher.
his is referring teacher, right? So this teacher and his are somewhat slightly more related than say teacher and say some other word, right? Or teacher and home. Okay, so this is the teacher's home. So how is that relationship? So how does the main problem with one hot encoding is that one hot encoding does not capture the relationship between words. Okay, and that's a big drawback, because if you take any two words, they are going to have this entry 1 in different places, okay? And there's really nothing that you can do when it comes to comparing them. Okay, so how do we generally compare vectors? So how do we,
Cosine similar.
yeah, so we'll come to the cosine similarity, but what we are so far used to seeing is distance, right?
Distance, yeah,
So
distance
Euclidean
of
distance.
Manhattan. Distance.
Yeah, so that is something we are used to doing. We are also used to doing angle between. So these are two things that we use to compare vectors, right? So if the distance is small, then we say that they are somewhat very close to each other. If the angle is small, we say they are close to each other. Unfortunately, the distance is same for any two vectors, is what is meant in the slides, right? You might have seen this. So the distance is what? For any two one-hot vectors,
It's root 2.
it is 2, right? It is always 2. So using distance, you cannot say anything about two one-hot vectors. Angle, what is the angle between any two one-hot vectors? Different one-hot vectors. X dot y, that will be always 0, right? So 90 degrees.
So distance will be root 2 or 2.
Root 2, sorry, yeah, root 2. Okay, distance will be root 2 and the angle will be 90 degrees, meaning any two word vectors or one hot vectors, different one hot vectors, will be orthogonal, right? So there's very little that you can take from one hot encoding, okay? Which is why we need to look for other representation schemes, other ways of representing words, okay? And the logic is, so alternative, okay? So one hot encoding is now thrown out. It's not going to be, we have already seen that it's not useful. So we need to look for alternatives. And the basic idea, if you understand this idea, this will help you with in transformers later on also. And this is a very nice sentence, right? Around maxim. A word is known by the company it keeps. Okay, so there's a good proverb that you must all know, that you are known by your 5 friends who surround you, right? So if you want to know a man, go and ask who his friends are, or go speak to his friends, right? So the closest people that you move with, kind of are, on an average, they represent who you are. So similarly for words, if you want to know what a word is, or if you want to get a sense of what a word is, you should go and look at the company it keeps, right? So the company of a word, right? Or what is a company? The words that surround a given word, right? That is called context. So context is nothing but the surrounding collection of words, okay? Now, this is where things become slightly tricky. So I'll just give you an example of what are called word senses, right? So this in this NLP, there's this idea of word senses, which is a senses. So the same word could have different senses. Okay, I'll give you 2 sentences, and you can tell me what these senses are. So I read 5 pages of this book. That is one sentence. Can you book the tickets? Okay, so what stands out in these 2 sentences? Do you see what is?
Book is common, but context is different.
Yeah, book is common. Okay,
Same word with different meanings.
yeah, so different meanings, right? We call these senses, word senses. So here the sense is the physical book that you read, and here the sense is, it's a verb where you are actually doing the task of booking the ticket, right? So this becomes a big problem when you actually look at simple representation of words, right? So in the one hot already we have thrown it out, but I hope you see the relevance of this maxim, right? A word is known by the company it keeps. So what allowed you to determine a particular sense for this word book here. These verbs, right? So this was important. Okay, even if I had not shown you this piece of text, okay, and I had somehow smudged this off, struck this off, you would have still managed to figure out that book here represents the physical book, right? So what you see is that the context determines the meaning of a word. Here, likewise, if I had smudged these things and had only retained this word, you would have figured out that the book here means the verb book, okay, and not the physical book. Okay, so this is what I mean by the word is known by the company it keeps. Okay, so another important point is if you extend this idea, so words that occur in similar context, okay, have similar meanings. Okay, so notice that we are using the word similar, not same. Okay, so again, once again, you see the interplay between contexts and the actual words. So this whole thing is called distributional hypothesis. Okay, so this distributional hypothesis. What do we mean by this? By looking at the distribution of words, the way the words are distributed and the similarity between a word and its context, we can actually learn a representation of that particular word. Okay, so if I want to represent book using a vector, I should somehow take into account what comes before it and what comes after it. Okay, if I just do something like this where I place a one in one location and then ignore all the other words, that is not going to be useful. Okay, so I hope this idea is clear to you. Okay, so that brings us to what are called word embeddings. Okay, and we will look at 3 cases so of learning or of how to learn these word embeddings. One is using this co-occurrence matrix. So these are what are called count based methods. There is the other one which is using prediction based methods. So this comes in the bracket, but what goes inside that is continuous bag of words model. So this is another method that can learn word embeddings, and the final one is what is called skipgram, right? So both of them are prediction based methods. Okay, so the skipgram SIBO, I think they are both kind of clubbed together in this very famous algorithm called word to vec. Okay, this was a very sensational piece of technology that was developed very early on in NLP once neural networks came in. Okay, so both from an exam point of view and from all assignment, grade assignment point of view, we will focus on these 3 methods. All right, so first thing is we have already established this fact that we have to study words and the context in which the words appear. Okay, so we build what is called we construct what is called a co-occurrence matrix from the corpus. So we already have a corpus, remember, and now we are going to construct a co-occurrence matrix. So each word, okay, so each row rather is going to correspond to a word, and each column is I would say target. I'll call this a target word, and each column is going to correspond to a context word. So maybe we'll try to build that for this corpus. This corpus is perhaps too big. Let me make it smaller. Can you tell me some very simple sentence that will
So
allow?
the next second sentence is in that core matrix you have mentioned that will be there.
Which one?
That second point in core matrix, so current matrix you have mentioned, right? There each row that would have.
Sorry, I didn't get it.
No. The each row is going to be right. Their repetitions are there, so we can that sentence itself we can take.
This itself,
Yeah, correct. Many repetitions are there and
okay. All right. So each row is going to correspond to a target word. Each column is going to correspond to a context word. Okay. So what will be the vocabulary here? See, the point is I want a small vocabulary, small fellow, not a big one. So each row is.
No, sir, this is too big, sir. Make it small, sir. Matrix.
Something that's like very, very, very small. So this is good. Okay, I already have 3. Maybe I'll have 2 more words. That's all. I don't want something more than a 5 cross 5.
Good but difficult.
This is good but difficult. That will be just one sentence, right? So is this good? This is great. Good is great. Okay. So the vocabulary is now this is good, great. That's all. Okay. 4 cross 4. So we'll just use the same context and vocabulary. So what we do is we need 4 cross 4, right? So this is 4 cross 4. So this is okay. This is good. These are all context, okay? And these are all words. So this is called a co-occurrence matrix. So how are we going to fill this? So we look at what is called a window, right? So we have already seen this moving window approach. So we are going to look at a window surrounding the word. Okay, so this is the word, mind you. This is the word, and these are all hopefully words that appear in the window surrounding this word. Okay, these are all context words. So this, when you have a target word, so when you have a target word, a window of size 1, let's start with the window of size 1, would be some word here on the left and some word on the right. This is a window of size 1. Usually we have one on the, so whatever size you mention here, you look at left and right. Okay, so a window of size 2 likewise will look like you have one word. So there are 2 words on the left, and then you look at 2 words on the right. Okay, is this window idea clear? What we mean by? So let's look at now. Let's build a co-occurrence matrix with window.
Sir, why we need window?
Because context cannot be infinite, right? So you can't look forever back. You have to restrict the region in which you look back or look forward. Okay, so that region is what is called the window or window size. So see, if the window size is infinite, right? What does that mean? Every word co-occurs with every other word. So that is not meaningful, right? So for instance, here, how do I put that? That Einstein thingy was there, right? But did I delete that or yeah? So if you're looking at Nobel Prize, right? And I'm looking at a window of size, let's say 4. So no, this is the word. Then these are all. So this is 1, 2, 3, 4. Okay, this is left 4 and right 4, left 4. So this is going to be the window corresponding to the Nobel word. Okay. Now, if I look at a larger window, like a very, very large window, then I would be including words such as also, who, right? I don't want all that, right? So what is relevant to me is captured best by the local context or surrounding that word. So Nobel is closely related to price, closely related to physics. We know all that. Perhaps year, right? So every Nobel Prize is associated with some year. So these are all context proper to me. Okay, but something like for, known, okay, is not really a context word, right? I won't call it a context word. So that's the reason
This
you are.
number is not a word, right, sir? 1921.
Sorry? No, technically it's a word. So that is still. So I'll see the word that we use colloquially is different from the word that is used in natural language processing. So this is also a word.
Okay, sir.
Okay. So context, remember, is something local. So the, the statement that I made earlier, right? A word is known by the company it keeps. So if you want to know the company, you can't go looking very far away from you, right? So your company is something very local. Okay, so this, if you start with the window size 1, this, remember, the word itself is not a part of its window. Okay, so you are not going to say that there is 1 here. No, this is 0. Okay, is the word is occurring in the context of this.
Yes, sir.
As this
One.
yes, right? So this will be 1.
One.
What about good?
0.
Okay, so in fact we are not yet done. So we have to look at all 4 sentences. So this is okay. It is also here, right? This, remember, you have to look at the word wherever that word appears. You have to look at a one context window surrounding that word. Okay, so therefore, what will this be?
2.
It will be 2. Okay, and what about good? 0, right? If your context window size is 1, you can't help it, right? So if the window size had been 2, then good would have been a part of your co-occurrence mean. That
No,
would have
why you have
ended.
not taken
But in the
why
next
you not taking
sentence,
is this?
Oh,
Taken
sorry, I
is
missed
this
that. Yeah, sorry.
second sentence.
Yeah. So good is that. Sorry. Yeah, this good. Okay, so yeah, that is there. Anywhere else that this and good are next to each other? Okay, this great is not there, so that is 0.
No,
Now we
no,
come.
sir. I am telling that is this. So then is will be 3, na?
Oh, nice. Yeah. Sorry, that is correct. Yeah, so this is, this is, this is, yeah. So 3. Okay, good is only 1, great is 0, right? Great is 0. Okay, what about is this? This is the word now. Left and right, 1, 2, 3 again. Okay. So in this case, you will kind of get something that's symmetric, but not always. So here it's 3. Is and is 0. Is and good. You have 1 and 2,
So,
right?
2.
sir, I was a question.
Yeah.
Do not be consider right and left like that. We will not consider only neighbors would be considered.
Right and left.
Like for example, for the first row, this with an is right. So this is followed by an is or a good or a great. Like that will be mentioning it. Or first row will represent right. So that is the representation of this is followed by an is will represent two occurrences. Like that, it will be representing the co-occurrence matrix, or this is either followed or been ready. Before it has an is, like that.
See, there are two things, right? One is called the target word. So whatever is there in the row is the target word, and everything in the column is the context word. So when this is the target word, you are going to look to the left and right of this for context words. So nothing is there to the left. To the right, you have is, right. So how will you update your matrix? Uh, you will update which entry? You will update the entry corresponding to m of this and is. So here, this is the context. Sorry, this is the target word. This is a row. This is a column.
Okay, so is can be anywhere.
Left or right, yeah. So the window is kind of on both sides.
Will not be considered left and right. Like
No. Yeah. In this case, we'll come to a situation where in CBOW, right? We'll come to the CBOW where by window I will only refer to words that come to the left. Okay. But that's a special case. For here, in this co-occurrence setting, window means both sides. Okay, so let's quickly finish this. What about is and great?
2.
2. What about good and this? 1 here. Only 1, right?
yeah, one.
Only 1. Good and is 1, 2, right? Good and good 0. Great. Okay, so I'll just maybe slightly change this here and make it great. Okay, it need not be grammatically correct. So good and great don't come together, right? So they are 0. Great and this do not come together. Great and this come twice. Great and good come. They do not come together, right? Okay, what about great and great now?
1.
It's a bit tricky, right? So if this is the word, then this occurs in the context. So you'll that will be 1. But you can also consider it the other way, right? So it's a bit tricky, but mostly we won't ask things where this kind of repetition happens. But I just wanted to show that you can have the word and context as the same thing. Okay, you should not be confused by that. Okay, so is the co-occurrence matrix clear to you?
Yes.
Okay, so this is the co-occurrence matrix. Now, what next? So this is a very small co-occurrence matrix. Typically, a co-occurrence matrix for a large corpus, right, or will be of shape, say 50,000 cross 50,000. Okay, and what does that mean? This means the following: each row or each column will have a large number of zeros. Okay, this is inevitable because if you think about it, your context window is maybe 5 words to the left, 5 words to the right, and there is no reason why a given word has to share the company of a lot of words in a given context, so in a given row, right? So I hope you see that every row, if you take every row, most of the entries will be 0. Is that fine? Here it's not the case because the corpus is small, the vocabulary is small, but generally the corpus is huge and vocabulary is going to be huge.
Sir,
Yeah.
aren't the two great are different? One is the target and one is the context. So I thought like this.
So this is that when this is the target, this is the context, and then you should also consider this being the target and this being the context, right?
Okay, sir.
So that's why we add two here. Yeah, if this is confusing, we can go back to 1, but this clear, right? Why this is 2?
Yes, sir. Yes, sir. Now clear.
Okay, so each row will have a large number of zeros. So what this means is that the matrix is sparse. We call such a matrix sparse. So why is sparsity a problem? So what are we trying to do? Remember that we are trying to represent words as vectors. Okay, and if every vector that you can think of, if most of the entries are zeros, and if that vector is so long, right? So with 50,000 dimensions or 50,000 entries, that's not really helping our cause. Okay, so we somehow need to know the what's our aim. Our aim is to come up with a dense. We call this a dense representation. Okay, with fewer dimensions. Okay, so that's our main target, to come up with a dense representation with fewer dimensions. Okay, all right. So we go back. Okay,
So what is the importance of this matrix?
so this
If
is
the determinant is 0,
no. So we don't.
transpose.
No. So this is not a matrix. We don't study it from that context, right? So we don't look at it as, of course, this is a matrix, and you can ask questions like what is the determinant, what is the rank, all that. But they are not relevant questions here. Okay, at least the determinant is not very relevant. Rank, yes. Rank
Transpose.
transpose doesn't make a lot of sense, right? You are just flipping the context and the target words.
Okay, sir. Rank.
Rank will still make sense. We'll come to that when we do SVD. It will play a role, but otherwise, determinants not so much.
So
Yeah.
these matrices are nothing but the embedding representations, right?
So you could treat. See, the idea is to learn embeddings or learn representations for words, but then these are too sparse for our purposes. So we have to somehow find a way of making them smaller and denser.
So value addition words only will consider, right? That will be propositions will ignore like that.
Sorry, I didn't get it.
We can ignore propositions or
Even
some
then, right? So even so, they even
these
after
words.
removing all that, it will still be sparse.
Okay.
Okay, so this is the co-occurrence matrix involving only counts. Okay, only co-occurrence counts. But typically, what is done is we don't just use co-occurrence counts. So what we usually do is involve this concept called point-wise mutual information. So that formula is there in the slides. I'll just give you some intuition for why it comes up. Okay, so there are actually three things here. So there is what is called mutual information, and then there is point-wise mutual information, or PMI as it is called, and then there is positive PMI or PPMI. Okay, we are going to finally use this positive PMI or PPMI, but how do we get there? So that's the question. Okay, so what does mutual information mean? Okay, this actually comes from information theory. So we'll look at the basic idea. This whole thing is probabilistic in nature, right? So okay, how likely is it that two events occur together? Okay, or how much more likely is it that two events occur together than random chance? Okay, what do I mean by this? So let's go back to this piece of text that we had. Okay, I'm selecting two words. So I'll just copy this text again. Who won equivalence? Okay. So I give these two words to you. Okay, and then I also give two other words to you. This is pair 1. This is pair 2. Now, can you tell me something about pair 1 and pair 2?
Useful information in pair 2 is more.
So the occurrence of words in the context.
Okay, so which is
More,
kind of
more number of times.
so what I want to ask you is going back to this, which of these two pairs is more like random chance? I am just picking two words at random. If I just pick two words at random, will I get pair 1 or pair 2
Pair 2.
at random? Think about it.
Pair 1 will be random,
Pair
pair 2 will
1.
be an actual
Okay.
value.
So maybe I didn't phrase the question properly, but if someone has picked words at random, then that will look like pair 1. Okay, so this pair 1 is someone who doesn't know English, let's say, or who doesn't know anything about Mr. Einstein, right? If someone picks words, someone with no knowledge of the subject or of the world, right? Let's say they will end up with something like this, right? This, on the other hand, is someone with knowledge of the world and its connections, right? And what do I mean by that? And the connections of things contained in the world. Okay, so this is someone who has no idea about how things operate in the world, but this is someone who has knowledge of how things are related, what it means for first something to be a first name, second name, right? So that's what we mean by this mutual information. So when two events come together, okay, with a probability that is higher than just random chance, right? That how likely is it? How much more likely is it that two events can occur together? How much more likely is it that I can pick words Albert and Einstein together rather than, you know, the case where I get them if I randomly sample two words from the corpus? Okay, I don't know if I have managed to explain this properly, but maybe you will understand this. So X and Y are those two words. Let's call them word and context. Okay, maybe this is context. This is the word. Okay. So what is this formula? This is P of W comma C by P of W into P of C. This is what the term point-wise mutual information is. So what does point-wise mean? It means for one instance. Okay, one point at a time. So can someone tell me what this? So this is PMI of W comma C. Can someone tell me why this formula makes sense? What is the numerator telling you? What is the denominator telling you?
So denominator means the word when they are taken independently.
Yeah. So the denominator assumes that the word and context, these are the events, right? Word and the context are okay. Okay, if someone were to randomly pick two words, they will pick the word with the probability P of W, and independently they will pick the word C with probability P of C. Okay, if they had nothing to do with each other, if the word and context had nothing to do with each other, this is the probability of seeing W comma C. Okay, the numerator on the other hand is the probability with which the word occurs together with its context. Okay, this is the probability with which Albert and Einstein occur together. Okay, so now tell me, will this PMI be high for pair 1 or pair 2? Roughly speaking.
High for pair 2.
Yeah, high for pair 2, right? So that's what I want you to understand. So maybe we don't know exactly what it will be, but the mutual, there is like a lot of mutual information between the word and the context because they occur together. Okay, and therefore the numerator will dominate. It's not random chance. They are not chosen independently in this case. So this probability will exceed the denominator. Okay, so typically it's not just this ratio. Since we are dealing with probabilities and probabilities can be very small, we add a logarithm and the logarithm is to the base 2. Okay, if you look at the lecture, if you look at the lecture notes, the probability will be given slightly differently. What the prof has done there is he has expanded this. So the joint probability can be written as P of C into P of W given C. Okay, you can, it's just the chain rule of probability. So you cancel these two. So if you look at these slides, okay, I'll just take the formula from the slides. This is the formula from the slides. Okay, you should now be able to compare these two. Okay, okay. So yes, cancel the other part, which is also fine. Let me do that so that we have the same thing. So what was this? P of W comma C, right? W comma C by P of W P of C. So I can expand this as P of W into P of C given W. So now P of C will get cancelled. Sorry, P of W will get cancelled. And then you will be left with P of C given W. In fact, P of C given W doesn't make so much sense because context comes in some sense before the word, but anyway, it's all the same. So you get the idea, right? How we arrived at this formula, the PMI. Some intuition do you have now? Okay, I hope you got some idea of what this PMI is. So yeah, so what you now do is you don't stop here. What might happen is this could go negative, and one way to avoid that situation is to only retain positive values. So how do you enforce that? You just make this 0 comma PMI of W comma C and call that PPMI. Okay, so
So
now
what is in here? In what is doing? What is the in?
yeah, so that is just you're expanding your P of C given W. So it is easier to explain it using this formula itself. Okay, so what is this? This is actually log to the base 2. How often do word and context appear together? That's just the count of word, okay, divided by the total number of word context pairs. Okay, assume that this is some quantity n. P of W is what? The number of times W occurs. In fact, this will be divided by n, right? So this divided by n into, this is once again count of C context divided by n. So this, if you notice, this will simplify to count of W comma C into N divided by product of the two plots. So it's just a way to calculate these probabilities. These are empirical estimates of the probabilities, right? How often do you see W? Number of times that W occurs in the corpus divided by an estimate for the total number of words in the corpus. Okay, is that clear?
Yes, sir.
Okay, so anyway, this is all there. This whatever I have discussed so far, right, regarding PMI, PPMI, you can refer to chapter 6 in Juravsky and Martin. Okay, we will get a better clarity. Chapter 6, what is chapter? Yeah, chapter 6. Okay, so now, yeah, so what is the co-occurrence matrix now? The co-occurrence matrix now has these PPMI values. Okay, that is what you have. So now let's say your final co-occurrence matrix is of size vocabulary cross vocabulary, right? So that's what your final co-occurrence matrix will look like, where each entry is the PPMI value between a word and some context. Okay. So what next? This is still too sparse. Okay, I can't learn. I can't use vectors of size v. I need to shorten this. So this is where you enter SVD. So singular value decomposition.
So PMI means what is that?
PMI is point-wise mutual information.
Point-wise.
Yeah, so it's point-wise because you are doing it for every word context pair. So actual thing is called the reason it's called PMI is there is something called mutual information, which is nothing but the mutual information is just the expectation of PMI, right? So if you think about so this is PMI, right? So on an average, what is the information between this is an expectation, right? So expectation is what? Probability of that event multiplied by some quantity, right? So this is the expected information between word and context pair. So MI is called mutual information and is the expected relatedness between word context, right? You're averaging it out over all word context pairs. And since this is computed for one word context pair, this is pointwise. Okay, this is pointwise. All right. So where were we? So we were here, right? Your final co-occurrence matrix is still not sparse. Sorry, it's sparse, and there's you can't learn word embeddings from that, or rather, you can't directly use them as word embeddings. So what you do is why SVD, right? Your aim is to extract the essence of or extract the underlying relationship between words. Okay, so at the surface level, you are not able to see this from the co-occurrence matrix, but the hope is maybe there is some hidden structure. Okay, and one way to extract that hidden structure is to use singular value decomposition. And what SVD does is it gives you SVD gives you a good low rank approximation to a matrix. Okay, so what is this low rank business? Uh, so what is rank? Do you remember what rank is?
Non-zero rows.
Okay, non-zero rows in the row echelon form, but so let's look at this matrix. So what is the rank of this matrix?
1.
Okay, why is the rank 1?
So because last one is similar to it, so it will be 0 again.
No, all the vectors are a multiple of 101.
Yeah, so there is effectively, there's only one vector. Okay, or rather there's only one useful column.
So is it like biases?
It is kind of right. So yeah, you can get there, but yeah, it is the basis. The size of the basis of the column space is the rank, right? That's the technical definition. But what I am driving at is more of in terms of information, right? So in terms of information contained in the matrix. So the rank. Okay, so I'll put it this way. The rank gives you some sense of the amount of information contained in the matrix. Okay, what do I mean by that? So this is a 3x4 matrix. The rank is 1. What do I mean by that? Effectively, only one column is useful. All the other columns are kind of copies, replicas of this column. One is multiplied by 2, other is multiplied by 3, third, fourth is multiplied by 4. Okay, 4 times the first column. That means. So if you have a matrix A, so if you have a say vocabulary is 10,000, right? So if you have a 10,000 cross 10,000 matrix, and if you can approximate it with a maybe 50 rank matrix, right? A matrix of rank 50. What you have done is you have kind of compressed the information contained in A into a smaller matrix, okay, which has rank 50. So you're kind of what you're doing is I don't need 10,000 columns to capture the information present in A. I can do it with just 50 columns. Okay. And if you can do something like that, then you have achieved what you're looking for. So you have achieved some representation for your words. You can get a representation for your words, okay, which is small in terms of the number of dimensions involved, and it is also dense. Okay, and in the process, you would have uncovered. So in the process, you would have uncovered the latent structure or relationship between words. Okay, so in approximating this matrix A using some version of the first column, what have you done? You have found out the relationship. It will help you find out the relationship between column 1 and the rest of the columns. Do you get that idea, rough idea? So you'll have to put all these things together. So is all of this somewhat convincing?
Yes, sir.
Okay, so you should go back to MLT, right? So where Professor Arun would have mentioned that compression is
Comprehension.
comprehension, right? So that's a very important phrase. When you try to compress the data, what you're trying to do is in the process. So in the process, you understand some essential aspects of the data, right? So which are like rest of it is fluff, superficial. But if you can compress it sufficiently without losing too much information in the process, you are going to recover some hidden structure in the data. Okay, so that is SVD. That's what SVD does for you. So now what you are going to do is, now the rest is, let me just use whatever, okay, Prof uses X. So So let me also use X. So X is your co-occurrence matrix with PPMI values. You can produce an SVD that's going to look like this. So this is U sigma V transpose. Okay. So you have to know what the shapes are. So X is itself of size V cross V, and sigma is of size. So in this case, this is also going to be V cross V, but SVD actually works for rectangular matrices also, and V is also V cross V. Okay. So this is how SVD is going to look like. But is this enough? What do you do from here? You extract a low rank matrix from this. Meaning, how do you do this? You retain the first k columns of X, sigma, and V. Okay. So you're going to call that resulting, and then you'll multiply them. So I'll just write this as X hat is going to be U hat, and sigma hat. So can someone tell me what U hat, sigma hat, and V hat are?
Orthogonal matrix.
Okay. No, what I meant was what will be the shapes? So what will be the shape of U hat?
V cross
K.
V cross K, right?
K.
You're only retaining the first K columns. So what about the sigma? Sigma hat?
K cross K.
No, only K cross 1 or 1 per.
So this is a diagonal matrix, right? Remember, so
Oh,
this will have K entries on the diagonal, K singular values. Okay, and what about V? V hat?
K cross V.
K cross.
K cross V, right?
but sir, should we not take V transpose? V hat transpose?
You're right. Sorry. This is V cross K, correct. Okay, so this is what it's going to look like. Now, interestingly, there is this form of X hat. You can express as X hat as sigma I equal to 1 to K, sigma I ui vi. Okay, so where vi transpose, right? So where ui is the ith column of what? Sorry, it's not theta. Okay, from the left, vi is the ith column of V, and sigma is the ith singular value of uh, the matrix X. Okay, so this is a rank K. So this is the what is X hat now? We call it the best rank.
So sigma is sir scalar now.
Yeah, sigma I is a scalar. Yeah. So what is sigma I actually? If you look at sigma, this will actually look like this, right? So this will be sigma 1, sigma 2, this will be d dots. Sorry. Okay. So on till sigma, how many singular values will it have? It will have actually sigma v, but then some of them will be 0. There will be only as many singular values as there are the rank of the matrix X. This is how capital sigma will look like. So this X hat is the best rank K approximation of X. Okay, is this clear what we are trying to do?
Yes.
Okay, so now finally we can extract our word embeddings. So our word embeddings, embedding matrix, right? And context embedding matrix. What is that going to be? That is going to be U sigma, or I'll use these terms like U hat, right? So let's first look at the word embedding matrix. This is going to be the word embedding matrix. And what is the shape of this matrix going to be? This is V cross K. This is K cross K. So this will be V cross K finally. Okay, so I'll call this W. So every, this is what is finally important. So every column of W, what is that? Corresponds to a word embedding. So for example, if you go back to this, where is our context that we were working with? So if you had this as the vocabulary, and you ended up with a W, the W here will have shape 4 cross, let's say 2. Okay, this K has to be less than the dimension of the vocabulary, or size of the vocabulary, right? It can't be more than that. So maybe we managed to reduce it to 2 dimensions. So this would be 4 cross 2. So it might look something like 4 cross, sorry, 2. What am I saying? Yeah, each row, sorry, not every column, should have corrected me here. Every row of W corresponds to a word embedding, correct? Is that correct? Are you with me so far? So W might look something like this, right? So I'm just making things up, right? So the first one would be the word embedding. So the vector 1, 2 is the word embedding for which word? Which word in this case? This, right? Okay, so likewise, this is word embedding. Now you'll have separate vector for context embedding also, and that is nothing but just V. So that will be of shape, as we already saw, sorry, V hat. Okay. What is V hat's shape? We saw that V hat was mod V cross K. And once again, every column, not every column, every row will correspond to the context embedding for one of the context words. Okay, so in the lecture you would have seen, why does this make sense? So Prof would have discussed this. So why does this make sense? So he would have invoked this idea of pairwise dot product between words. Okay, did you understand that part? Or should I go over that also? Right? So XX transpose, you would have done XX transpose. Did you get that part in the lectures? Why Prof does XX transpose?
Yeah, so the professor was saying that it is an cosine similarity between the word. That's
right.
also.
Right. So this is the cosine similarity between the word, and then if you kind of try to approximate this with U sigma, so if X, so U sigma V transpose, right? That's the SVD, and you have U sigma V transpose. So this, if you take the transpose, this will become V sigma transpose. U transpose, right? V transpose will become the identity matrix because these are orthogonal matrices. So you'll end up with something like this. So this is nothing but U sigma into U sigma transpose, right? So up sigma, sorry. So U sigma, remember we are just, that was our word embedding, right? So W transpose. So what does it do? You could think of the word embedding matrix that we obtain as being related to this pairwise dot product between words. Okay, that's what we want to kind of preserve because words with a higher dot product tend to be more related, right? That's our whole idea. So in fact, I probably didn't mention that earlier, but that's the idea. Okay, this he says this is the intuition behind retaining U sigma as the word embedding matrix. Okay, or U hat sigma hat. So it's not U sigma itself because this will be the full blown SVD. What we want is only the first K entries. Okay, is it clear so far?
Yes,
So
sir.
is this k equal to rank or is it something different?
It is less than or equal to the rank. Okay, it cannot be more than the rank because more than the rank it won't make sense. But
Yes.
typically it should be something less than the rank. So maybe say if your vocabulary is 50,000, if vocab size is say 50,000, you might choose K to be say 200. So all your word embeddings will be of size 200. You would retain the first 200 rows, sorry, first 200 singular vectors and singular values to construct the embedding matrix, which is U sigma. U hat sigma hat. Okay, so remember this is the embedding matrix, not U sigma. So U sigma, full blown U sigma will give you V cross V once again. Okay, that's not what you want. You want only V cross K. For that, you have to retain the K columns. Okay, so I think we are already late. Not late, but if we start CBOW now, it will be a bit hard. So, shall we discuss these two tomorrow?
Yes, sir. Tomorrow when?
Tomorrow, same time, is it fine? 8:30 p.m.
Yeah, yeah. It is fine. For me, it is fine, sir. I don't know other.
Okay, whoever is here, if you want to join tomorrow, is 8:30 p.m. fine?
Yeah.
Okay, sir.
Okay.
Okay, then we can
Sir,
meet.
it is needed, sir. I mean, so you want to learn it, sir.
Yes, sir.
Yeah, yeah. So we can do CBOW and skipgram. So in skipgram, basically, we'll only discuss this thing called negative sampling. Okay, so the others are kind of I should actually take a look at them, but we'll first learn these two properly: CBOW and skipgram with negative sampling.
Sir, one thing I don't understand in the Siva, okay, so professor is saying one is word, another is context. But here it is very clear in the SBD, but Siva somehow it is not very clear. Which is word, which is context.
Okay, yeah, CBOW we'll discuss. Yeah, CBOW we'll discuss that tomorrow. So word is basically the thing that you're predicting in CBOW. So what you are predicting is the target word, and what helps you make the prediction is the context. So you use the context. So you use the context to predict the word. So that is SIBO. In skipgram, it is the reverse. So what you predict is the context word. Or so it's not strictly speaking, that's not what you're doing. You are what you're predicting is a given pair a word context pair, or is it a word out of context pair? That's what you're predicting actually. But for simplicity, what you're predicting is the context, and what helps you make the prediction is the word. So you use the word and predict what is around it. That is skipgram.
So in English, what is meant by the word actually? So that I am confused. In English, word means word, but here it is word means something different.
Yeah, so see there are, so in the textbook if you see that they clearly distinguish between context and target word. So there is something called context word and target word. So what would this look like? So if you have, this will be context word 1, and then there's some other context word 2, and then there's a target word. This always is at the center, and then you have, so this is like left 1, left 2, right? And then you have the right context. So you have, this will be right. So yeah, so in SIBO, what is happening is you are given the context and you have to predict the target.
Sir, context means sequence of words.
Not sequence. So this thing is called bag of words. So bag of words means the sequence order is not relevant. What is relevant is the collection of words, right? So that's what bag of words means. So you can search Wikipedia for the bag of words assumption. So the basic assumption is that ordering is not important. Okay, if you put things in a bag, is the order retained? So let's say you have a handbag and you are putting or some 5 items into it. You may put them in some order, but then inside the bag, do you think the order will be retained?
No, sir.
Oh, right. So that is what it means to have a bag of words. So we don't really care about in SIBO, we don't care about which is the first context word, which is the second context word. All that we care about is these two are context words, and then I predict the target word. So that is SIBO. In the skipgram model, what will happen is I have access to this, okay, and then I will what I will do is I will ask the question: are these two words context words, the context target words? And I will also, in the case of negative sampling, what I will do is uh, will generate some non-context words also. So that's what we mean when we say negative sampling, right? You are sampling words that are not a part of the context of the target word. And then the question you ask is, given a pair, is it a context word pair or is it a negative context word pair? That is the question you will ask in skipgram. Okay. So whenever you see in the lectures, whenever you see simply word embedding, you should assume that it's the target word embedding. So target word is always this thing that is at the center, and context is whatever surrounds the target word.
So when the professor is doing the lectures, he doesn't pass the context directly. He said that context should be learned. So that actually create the problem. Probably I don't understand that purely. Yeah. So
Context,
tomorrow we can discuss on this. Actually.
yeah. Tomorrow we can discuss these two.
Yeah.
So
Yeah. Yeah.
okay then. Yeah, we'll meet again tomorrow.
So,
Thank you, sir.
Yeah. Yeah.
so in PMI we're using log of 2, right?
Log to the base 2. Yeah.
But in lectures there is no mention about that. Base
Yeah.
2.
So stick to log to the base 2. Okay. We should use the, so usually when it comes to entropy, mutual information, all these things from information theory, right? You typically end up using log to the base 2.
Okay. So in exams it will be mentioned, right?
Yeah. So in exams it will be mentioned.
Okay.
Okay, then we'll meet again tomorrow at 8:30.
Thank you, sir.
Thank you, sir.